In recent videos, I've looked at Q-learning, deep Q networks, and Q-star, and how it could lead Tesla to better full self-driving. But recently, I thought about AI Day 2022, yes, 14 months ago, and I realized there were actually hints in that video about what Tesla was thinking about over a year ago, and then we can speculate on what they might have done since. Let's take a look. Hey y'all, it's Dr. Know-It-All. This is part 3 or 4 in an unintentional series on deep Q networks, Q learning, Q star, the whole thing about OpenAI and the potential for an artificial superintelligence, Tesla and their full self-driving and how that works with it. And also over a year after the last one, another episode about Tesla's AI Day 2022. And while I believe I touched on this part of the talk in my previous talks, I hadn't really thought through it very carefully. It's one of those things at the time it didn't mean as much as it does now when I've put together a bunch of the other pieces in other videos. So I definitely want to get into this. So I'm going to go through about a 10-minute section that Paril Jain, and I'm sure I'm mispronouncing his name, I'm really sorry about that. But anyway, that he talks about planning and Tesla's full self-driving. And if you listen carefully, and I'm going to pull this out, of course, you can hear the references to DeepMind's research on AlphaGo, AlphaZero, and MuZero that I just covered recently. And I will leave a link to a bunch of these videos right here, and also will put them in the description so it's easier for you to click on them. I highly recommend watching all of the videos if you haven't already watched them to get a full sense of what's going on, because I'm going to skip over a few things assuming that you already know them. So without further ado, let's get to his part of the talk. It's about 10 minutes, and it starts at about the hour and 4-minute mark. And by the way, if you look here, I am somewhere in here. I'm not exactly sure because I can't even see the back of my head, but I think this might be me here, and this might be my wife, this might be Lane. So I'm not quite sure, but I remember being like right in this area. So somewhere in there, that's where I am. But so I was watching this live, which was very cool. And I'm really hoping for AI Day, 2023 or AI Day 3 to come up soon, because obviously it would be great to see that in person. And of course, to get a more official sense from Tesla on how they've matured this technology with version 12 of their software and things that they've been thinking about since this actually happened, right? If we can believe Walter Isaacson's book, it sounds like the skunk works for version 12 end-to-end full self-driving training and everything started at the end of 2022, so less than a year ago. And this, of course, was about 14 months ago. So version 12 of the software wasn't even something that they'd explicitly thought about yet. But after looking at deep Q networks and Q-star and MuZero and everything, I can actually see the stepping stones for what would have gotten them to the point where they started to think about doing fully end-to-end training. So without further ado, let's take a listen to what Paril has to say.
Hi all, I'm Paril Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. So a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one.
So I'm going to turn down the volume and I'm going to show this video section really quickly again, because this is what he bases his talk on. So you can see here that what we have is a complex interaction of different things. You've got the ego car that's trying to make a left-hand turn into an intersection. You've got cars that are passing, and then you've got this pedestrian over here, which, human beings, lovely. This guy is walking his dog and they just walk out into a multi-lane road without a crosswalk or without the, right of way of being able to do this. But obviously your car can't hit the person even though they're in the wrong. So you can see after this car goes by here that this person just starts walking out. It was hidden from view from the vehicle. And so this is a complicated thing for a person, of course, too, is like, what do I do? Because there's a car coming from the right, as you can see, and there's this car also turning. So how do I negotiate this entire situation? And if you watch my recent video on MuZero and DeepMind and how that could lead to full self-driving star, you can see that what this is this is effectively like a game of super complicated chess. You've got all sorts of branching decisions that can happen, right? You've got a decision about whether to cut off the pedestrian. You've got a decision about whether to go around them. You got a decision, I guess you could go backwards. You could try to back up your vehicle at some point. You could decide to bail and make a right-hand turn instead. There's lots of different competing possibilities here. So you've got this branching state space, just like in a game of chess or Go or something, but it's way more complicated than the branches increase very, very rapidly, and you don't have a lot of time to make this decision. That's another thing. Even with a game of chess or something, you usually, even if you're playing with a clock, you have 30 seconds or a minute or something like that to make a move. This thing is like ultimate speed chess with ultimate huge board with lots and lots of different moves. So you've got a really big action space, and you've got a really big potential for reward or punishment depending on what you do in this particular situation. And so if you watch that video, you'll have heard me talk about the policy network, the value network, and of course the reward network, the reward function, which is telling you how do you evaluate what's going on. So the reward in something like a chess game is win or lose. It's a very, very sparse reward system. In something like an Atari game, you get points and you figure out, oh, I just increased my points because I passed this car and did something good, or I removed points, or I blew up and that was a bad thing. So you have a dynamic reward situation here. And in this, you've also got a dynamic reward situation. You've got this reward situation that is changing constantly, but then you've got a policy that the policy is, what does the car do? Does it make this left turn? Does it continue on? Does it more aggressive to get in front of the pedestrian? Is it less aggressive to get behind them? But then what does it do about the cars that are coming from the right? Those kinds of things. So that's a value system. It's a way of evaluating the situation. And then the reward is, how do I basically score this game that I'm playing here? And it's a game of life, of course. You don't want to take any chances. If you lose a game, no big deal. If you lose a drive, it is a big deal. And there are other factors as well that Paril's going to talk about in just a second. So let's continue listening.
And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal and lateral profile. Now, obviously, we are being a jerk to the pedestrian, and we would spook the pedestrian and his cute pet. We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing: stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents pass. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents.
So as you could see, as I was talking about, you have all of these potential trajectories, and it has to pick between them, and it has to do it very rapidly. What Paril talks about here is the higher order derivatives. Is what he's talking about is latitudinal and longitudinal acceleration and jerk. In other words, how uncomfortable is this for somebody in the vehicle? So jerk is just what it sounds like. It's like if the car goes like or something like that, or really rapid acceleration or something. That can be very uncomfortable for the people in the vehicle itself, the ego car, the red Tesla right here. It can also be very uncomfortable. Like there's this version of the trajectory where it goes in front of the pedestrian and the dog. That's a scary sort of situation for the pedestrian and the dog. I would imagine that that guy would be very upset about this, even though ultimately it's his fault for walking out into a busy road without a crosswalk and not having the right way of walking. So anyway, even though, you would kind of have the right to do that, you don't want to be a jerk to them. So those higher order derivatives are the kinds of things that you have to pay attention to. It's not just the trajectory, but how do you do it? Do you do it smoothly and slowly and carefully, or is it high acceleration and especially high jerk, which is the next order derivative on top of acceleration? You don't want to be jerking the passengers around in the car. You don't want to be accelerating, especially latitudinally, like around a corner, that kind of a thing, very, very rapidly without warning the passengers in the car. And you certainly don't want to do it around a vulnerable road user like a human being.
Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far because you will miss out on a lot of valid interactions. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem.
So joint trajectory planning is basically what it sounds like. You're trying to figure out the trajectory of all of the different elements in the scene. So that's not just you in the ego car. That's also this blue car that you can see. That's the pedestrian and his dog. That's the other vehicles up here that are facing you. That is these other cars that are going to come in from the right in just a second, and potentially cars coming in from the left. So it's got to figure all of that kind of stuff out. And it has a very, very tight time constraint. We're talking about, less than 10 milliseconds it has to make a decision, or less than 1/100th of a second. It's got to do all of this planning very, very rapidly. So it can't go down this gigantic search tree. It can't go down this almost infinitely broad search tree without pruning it in some intelligent manner. And again, just like with AlphaGo, what DeepMind had to do in that case was they had to figure out how to sort of weight the dice. They had to get the Monte Carlo search, the different possible trajectories that something could do, in this case a game, but in this case we're talking about driving. They had to figure out how to weight things so that you could guide it down the most likely path, the 2 or 3 most likely trajectories that it could take, not the 100,000 most likely trajectories. Too much space to search. So you have to start pruning things down very, very rapidly in order to do this in a real-time situation, which is highly constrained.
It will be close to order of 10 milliseconds, even after a lot of incremental approximations. Now, for a typical crowded, unprotected lift, say you have more than 20 objects, each object having multiple different future modes, the number of relevant interaction combinations will blow up.
And so here you can see what he's talking about is you've got 20 relevant objects, cars, pedestrians, whatever. And if there are 100 relevant interaction combinations, you're looking at some sort of exponential explosion of the decision tree. So it can't really work. Even if it makes each decision at 10 milliseconds per decision, it looks at each trajectory, that's way too slow. It could take it I don't know exactly what the exponential here is, depending on how things are working, but anything from the order of multiple minutes to the age of the universe to figure out the answer if it does an exhaustive search. That is obviously not workable. Neither one of them, even the shorter version of it, the car can't sit there for 5 minutes because the entire scene is different in 5 minutes than it was 5 minutes ago. So it has to make these decisions really fast, just like a human being does in the same circumstances.
The planner needs to make a decision every 50 milliseconds. So how do we solve this in real time?
So there's your problem. It's like playing a game of super complicated chess or Go, and yet you've only got 1/20th of a second to make that decision. No human being can play chess at that speed. At least I don't think so. Maybe there is some super speed chess player, but nobody's going to play a good game of chess at that kind of speed. You don't even have reactions that are that fast. But on the other hand, we humans are able to do this kind of interactive, tree search pruning in our brains that are pretty darn slow in this kind of time frame and drive under these circumstances reasonably well. This is a decision that a human would ultimately make, is to, go around all of these vehicles and not cause extreme acceleration and jerk and stuff like that and slot into that situation. So a human can handle this, but this is really complicated stuff we're talking about here.
We rely on a framework what we call as interaction search, which is basically a parallelized tree search over a bunch of maneuver trajectories. The state space here corresponds to the kinematic state of ego, the kinematic state of other agents, their nominal future multimodal predictions, and all the static entities in the scene. The action space is where things get interesting.
Okay, so as you can hear, one thing that they do is they parallelize this search. So they don't go down one and then another and then another. They look at a bunch of them at once. So that does speed things up. But the big thing here is that we've got S and A. We've got our state space, where we are right now, and we've got our action space, which is essentially what our policy network is going to look at. That's the kind of thing like, if I do this, what happens? If I do this, what happens? If I do this, what happens? Again, just like the moves in a game, just a super complicated game, and there's lots and lots of moves because there's one move every 20th of a second or so. So it's many moves, hugely branching tree, but it is just a sort of a tree search idea. But ultimately, this is just a tree search, just like something like AlphaGo would be using to solve a game of Go.
We use a set of maneuver trajectory candidates to branch over a bunch of interaction decisions. and also incremental goals for a longer horizon maneuver.
Okay, and again, that's worth touching on as well. Incremental goals. So that's that reward function. So remember that as we moved from AlphaGo to AlphaZero, when we were talking about DeepMind's thing in the last video, we added on a reward function as well. And incremental goals would be that sort of incremental reward function. So rather than waiting until the end of this entire maneuver, it can make decisions based on rewards in sort of real time as it makes like progressive amounts. If you think about it, a drive could be anywhere up to multiple hours, right? If you're on a road trip or something. So you can't just get one result at the end of the entire drive. You need these little fine-grained incremental results. So what you need to be looking at is horizons of a second or 2 seconds or 3 seconds and grading it based on the reward function for that sort of a time period.
Let's walk through this research very quickly to get a sense of how it works. We start with a set of vision measurements, namely lanes, occupancy, moving objects. These get represented as sparse abstractions as well as latent features.
All right, so sparse abstractions and latent features is a very important thing. I didn't touch on this enough with my talk in the last video about deep Q networks, but the really important part is that what they do in mu0 is they abstract out reality into a latent space, which is kind of a compressed, vectorized space of understanding the world, and they do the Monte Carlo search in that latent space. So what they've done is they've abstracted out reality. So again, if it's a game of Atari, you've got a bunch of pixels on the screen, and you have to interpret what that means in terms of like driving and game rewards and stuff like that. Here you've got a bunch of photons hitting cameras, and you have to abstract it. You can't just deal with millions and millions of photons. You can't make a decision based on that. So the first thing you have to do is abstract out that visual system into something that's more of a latent space. So you could think of it as having some objects like car, person, road, stuff like that. So it pulls it into a latent space like that, and then it performs that Monte Carlo tree search in that latent space rather than in reality. So that's a very important step that they have to take in order to be able to make this work. And DeepMind did this with their AlphaZero and their mu0. And what you can see is that Tesla is utilizing that sort of technique, except they're doing it in the real world as opposed to in something as simple as a board game or even a video game, which is much, much simpler than reality.
We use this to create a set of goal candidates. Lanes, again from the lanes network, or unstructured regions which correspond to a probability mask derived from human demonstrations. Once we have a bunch of these goal candidates, we create seed trajectories using a combination of classical optimization approaches, as well as our network planner, again trained on data from the customer fleet.
So this is definitely worth calling out. This is something I'm going to come back to at the end of the video after we finish this little video clip here. But here you can hear Paril is talking about how this is all trained on and utilizing the human feedback. In other words, the data from human drives to provide the full self-driving planner and reward system with what it's supposed to be doing. In other words, that value, the sense of like, what is my reward? What is the correct way to drive? All of that stuff is being provided by human drivers in this case. Again, 14 months ago. And again, this is very analogous to AlphaGo. When DeepMind originally trained their Go player that beat the best players in the world, they did it using a lot of sort of hand tuning heuristics. They added in a bunch of human information to help the thing along to get as good as it possibly could be. But when they moved to AlphaZero, they moved away from that. So let's table that for just a second.
Data from the customer fleet. Now, once we get a bunch of these seed trajectories, we use them to start branching on the interactions. We find the most critical interaction. In our case, this would be the interaction with respect to the pedestrian, whether we assert in front of it or yield to it. Obviously, the option on the left is a high penalty option. It likely won't get prioritized.
So here you can hear how he's talking about just this one interaction. And remember, there are dozens of interactions happening during this one maneuver. But this one interaction is, do I go in front of the pedestrian or behind them? That's a nice, simple, binary branch. It's like before or after. So it's able to make that decision, and it's able to look at the reward function, and the reward functions, including the acceleration, the fact that human drivers wouldn't go in front of this pedestrian normally. That kind of stuff gives it the sense that the higher reward is to wait for the pedestrian to go by and to go around after that person.
So we branch further onto the option on the right, And that's where we bring in more and more complex interactions.
And so again, you've got a binary branch, right? It makes a decision before or after the pedestrian, but as soon as you go after the pedestrian, then you have many, many more branches, because you can see that this blue vehicle back here is starting to come into the scene, and you're going to have to suddenly deal with that blue vehicle and another car behind them, and again, potentially a car coming from the left as well.
Building this optimization problem incrementally with more and more constraints. And the tree search keeps flowing, branching on more interactions, branching on more goals. Now, a lot of tricks here lie in evaluation of each of this node of the tree search. Inside each node, initially we started with creating trajectories using classical optimization approaches, where the constraints, like I described, would be added incrementally. And this would take close to 1 to 5 milliseconds per action.
So thus far, Paril hadn't really talked about how they made the decision internal to each of these branches, but you can see here that this was the original way that they did it. 1 to 5 milliseconds per action is pretty good, but it's not fast enough, considering how many branches and how much this entire situation blows up very, very quickly. And so he's going to talk next about creating these networks of values so that it's able to evaluate the potential without having to go all the way down each of these branches. And that, of course, is the advantage of a deep Q network, is that it's able to give you a Q table. It's able to give you a value table of the expected results of the end of a long string of decisions by just a single number. So you don't have to go all the way down. You can look very, very quickly. So instead of having to do these very, very deep searches, you can just go forward a step and you can go like, what is my expected result if I just go forward with this step by doing this? And it can give you that result much more quickly. So you can see the old system, too slow to make this work. New system is going to be much faster.
Now, even though this is fairly good number, when you want to evaluate more than 100 plus interactions, this does not scale. So we ended up building lightweight queryable networks that you can run in the loop of the planner.
So notice here what he's talking about is lightweight queryable network, or LQN. And what we talked about in the previous video, of course, was deep Q networks. So what we're looking at is something very similar to a DQN, but obviously they've made it even lighter weight so it operates more quickly.
These networks are trained on human demonstrations from the fleet, as well as offline solvers with relaxed time limits.
And again, here, analogously to AlphaGo with DeepMind, what you've got is demonstrations of humans. So in the case of Go, there was many, many games that people had played. Here, what we've got is many, many drives that people have done and similar circumstances. So you train on that, but you've also got offline solvers where you give it a lot of time to make a decision. So instead of milliseconds, it can take minutes if it wants to, and it can figure out what the best opportunity is and the best trajectory. Now, why is that helpful? It's obviously not helpful when you're actually driving, but what you can do is, if this queryable network, this LQN, is something that is a neural network, you can train those weights. And so you can give it this relaxed time limit where it can actually, kind of think about it for a while, and it can come up with a good solution. And then it can back propagate that into these numbers, these queryable numbers. And then the system in real time, when it's in inference mode, can call upon this and get sort of a single number that gives it an indication of how good the whole branch is going to be down it. So it's able to do these very exhaustive searches, or at least much more exhaustive searches, able to look down all these branching networks and everything and figure out what the best option is, and then put that into basically one single number that's just in a table that the computer in inference time can check on and go like, is this a good idea or not? And it's like, yeah, this is a good idea, or no, this is not a good idea.
With this, we were able to bring the runtime down to close to 100 microseconds per action.
So I'm going to move myself out of the way here to make sure you can see this, but 100 microseconds per action is an order of magnitude faster calculation than they were doing with the old system.
Now, doing this alone is not enough, because you still have this massive tree search that you need to go through, and you need to efficiently prune the search space. So you need to do scoring on each of these trajectories. Few of these are fairly standard. You do a bunch of collision checks, you do a bunch of comfort analysis. What is the jerk and axle required for a given maneuver? The customer fleet data plays an important role here again. We run two sets of, again, lightweight queryable networks, both really augmenting each other. One of them trained from interventions from the FSD beta fleet, which gives a score on how likely is a given maneuver to result in interventions over the next few seconds. And second, which is purely on human demonstrations, human-driven data, giving a score on how close is your given selected action to a human-driven trajectory.
So I kind of jumped over what Paril is talking about here. He's actually talking about training the light queryable networks here. So sorry, I got a little ahead of myself. But the basic idea here is this trajectory scoring is to create those numbers in the light queryable network to figure out what the best trajectory is by already looking at the solution space and knowing ahead of time what the right answer is. And so one of them, of course, a collision check just to make sure you're not going to hit something, comfort analysis to make sure you're not accelerating or jerking too much. But then interestingly enough, the interventional likelihood. So there's a whole other network that's like, did the driver, if I made this maneuver, would the human being intervene and take me out of full self-driving right now? That would obviously be a negative score and that would hurt the reward system. And then the last one would be kind of a parallelization, right? If you imagine you're creating this trajectory like this, and you can match that up to a human drive in a similar situation and say, how close was I to this at every single point? Did I make that maneuver almost exactly like a human did, or did I deviate significantly from the human? And if I deviated, that's also a negative reward as well. So this is the way that you train this network up. And again, you can do it with relaxed time limits, so it can actually be much more exhaustive. But you train this network up so it can kind of cheat when it actually gets to inference time, because it already sort of knows the answer because of all the training it's done.
The scoring helps us prune the search space, keep branching further on the interactions, and focus the compute on the most promising outcomes.
So again, we're talking about that rolling the dice, but having weighted dice. You're weighting the dice so that it's more likely to come up with the solution you think is the best than any other one. Now, you have to be careful here. You can't completely remove the explore part. You know, you're always in that explore exploit dichotomy, and you don't want to completely get rid of explore because there might be a weird move that you might be able to make that could actually be better than what you thought, but you want it most of the time to be coming up with something you think is the most likely solution.
The cool part about this architecture is that it allows us to create a cool blend between data-driven approaches, where you don't have to rely on a lot of hand-engineered costs, but also ground it in reality with physics-based checks.
So here you can see Paril starting to talk about getting rid of the human, tweaked things. So fewer heuristics that are put in by humans, more training, but it's still using human data at this point.
Now, a lot of what I described was with respect to the agents we could observe in the scene. But the same framework extends to objects behind occlusions.
And then Paril goes on to talk about occlusions, and then Phil talks about occupancy networks and stuff, and we've talked about that a lot. So that's the state of the art at the end of September of 2022. What might have occurred in the last 14 months is I think that Tesla could have gone, their full self-driving team could have gone from the AlphaGo sort of stage where you've got a system that has a lot of input. It's got human drives, human discriminators, how likely was it for the person to intervene, all of that kind of stuff that's being layered on top of these networks, to turning it loose to more of a mu0 sort of situation. And if you recall from the last video, mu0 started with the state network, the policy network, and the reward network were all sort of randomized. They were just created, from scratch without any real information. A lot of the hand tuning stuff was taken out, and the system was just allowed to play itself and play itself and play itself over and over and over again to figure out what the proper weights are in order to do well in the system. And as it turned out, it was actually better than the hand-tuned systems because you were taking away the necessity to look at human interactions previously to figure out what the best answer was. In other words, AlphaZero became better than AlphaGo and better than human players, any human player, and made moves that no human had ever seen before because it was not constrained by human information. So we could be looking with version 12 of the software, with Full Self-Driving version 12, that the system is not necessarily bound by human driving anymore. It's creating its own system. It's generating its own frames. It's evaluating all of that stuff on its own. And then you can validate eventually with human drives to make sure that it's not going completely off the rails, but it can learn at an extremely fast pace, again, that hockey stick sort of moment, because it's not limited to human drives. And when we got to the end of the last video that I was talking about, I was saying, look, we could be at a situation where these drives could become superhuman. They could be better than the best human because this thing is able to think outside the box, so to speak. And the reason why I wanted to call up this piece of the AI Day 2022 talk is that it begins to get into that space, right? It's in the AlphaGo state of things where they're actually basing all of this on human drives and everything, but the logical next step is to remove the human from the loop. And when we look at the CVPR 2023 talks that Phil and Ashok did, you can hear them talk about generative stuff where they're actually generating next frames and looking at that, where it's autonomously doing that. And that was the thing that made the connection to me. me. I was like, oh, okay. So what they're doing is they're moving from the AlphaGo sort of state to the AlphaZero/mu0 sort of state that DeepMind was doing. And they're working on a system that's divorcing this from the necessity to look at human driving data all the time, except as a validator, as a way of making sure that the thing is working properly in sort of more of a quality assurance and testing sort of phase. So in the end, we could be looking at these lightweight queryable networks, or a version of a deep Q network where it can prune the search space very, very drastically, again, in a sort of a latent abstracted space. So first it abstracts things from reality into a latent space that's very highly compressed and that the computer can deal with very, very quickly. And then it's able to do these Monte Carlo tree searches in a very, very directed way because it's got these deep Q networks or lightweight queryable networks, whatever it is. It's got these trajectory planners that are giving it a reward and telling it what the likely outcome is without it having to go down all of these branches, which means that something like this is really good at long time horizon tasks. In other words, things that take multiple seconds, not things that are just microseconds long. And so that's absolutely incredible for full self-driving, and hopefully we'll see full self-driving version 12 very, very soon and get more of a sense of that. But also, if you think back to the Optimus robot demonstration that they recently did, the one where it's sorting the blocks and everything, that's a long time horizon task as well. That's multiple seconds it's trying to do something, and you could see the person moving around the blocks and all of that kind of stuff. And so you can see how that could be very effective for Optimus as well. So again, everything that would work for full self-driving would work really, really well for Optimus as well. And I think, it's my inkling that what we're looking at here is that sort of progression. And again, if we layer on top of that, this Q-star idea of being able to more efficiently do this with lighter weight networks and the evolution of the A-star algorithm into a Q-star algorithm, we start combining all of this stuff together. We again could be at a state where full self-driving version 12 might not really need to be beta anymore. Elon did say back in August, he said, I think version 12 is not going to be beta anymore. I don't know that they, the Tesla legal team might not make that a possibility because they might be like, nope, we're going to keep labeling it beta. But we could be looking at a really, really major step change from version 11 of the software. And now, rather than it being magic, we can actually see the stepping stones as to how Tesla is actually building this thing. All right, I hope you enjoyed this rather geeky episode and found it fun and interesting and thought-provoking. If you did, please do like it so other people can find it. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon, my YouTube channel members, and of course my ex-subscribers. Thank you all so much for supporting the channel in any way that you can. And if you want to join any of the teams, just check out the links in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a new Tesla, a solar roof, a Powerwall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.